Okay, I wanted to take you through some Chapter 4 and Chapter 5 practice problems and kind of talk you through these things in the hopes that it'll help a little bit. So here we go. So let's look at this one. So among 500 randomly selected drivers in the 16 to 18 age bracket, 376 were in a car crash in the last year. If a driver in that age bracket is randomly selected, what is the approximate probability that he or she will be in a car crash during the next year? Okay, this is just a basic probability question. Just want to make sure you can do these things. So the way we do this is number one, you identify the sample space. And if you look at this, you'll see that we have these 500 randomly selected drivers. So this represents our sample space, right? We have 500 possible responses. Um, and identify the desired probability, which we're interested in the probability that he or she will be in a car crash. So the probability that someone from that sample will be in a crash. Okay, so the way we solve that is by choosing the number of drivers that were in a car crash, which we see is 376. Okay, and divide that by the total of the sample space, which we know there's 500 scores in there. So if we take 367 and divide that by 500, we get 0.752, and that is our answer. So there's a 75.2% chance that we choose someone that has been in a car crash, okay, or will be in a car crash in the next year. All right. Second problem. Okay, in a survey of consumers aged 12 and older, respondents were asked how many cell phones were in use by the household. And then we have a bunch of different numbers that is coming up. So no two responses were from the same household. So among the respondents, 213 answered none, 291 said 1, 369 said 2, 142 said 3, and 98 responded with 4 more. So a survey of respondents selected at random. Find the probability that his or her household has 4 or more cell phones. So this is very much similar to the first problem. The only trouble is we don't need to add, well, we need to add some numbers to get that total sample space. So we identify the sample space, which is going to be the total respondents. To get that, we need to add up all those numbers you see there. So that 213, that 291, that 369, that 142, and 98. And we do all that, and we get 1,113. Okay, from there, we want to identify the desired probability in the problem. So it's asking us to find the probability of 4 or more. And so we will look at the numbers, and we'll see right up at the last part of that statement that 98 responded with 4 or more. Okay, so the probability of that is we choose that 98, so choose the number of respondents who reported 4 or more, 98, and divide that by the size of the sample space, which we found to be 1,113. When you do that, you get 0.0881, and that is our answer, right? So an 8.81% chance. All right, number 3. A raffle is held in which 10 different names are written on slips of paper and tossed in a hat. Okay, names are then drawn one at a time without replacement. What is the probability of guessing the first 3 names drawn in the order they are drawn? Okay, so one thing to realize is that the numbers in this case are not independent. So that is, once you draw one out, it affects the probability of the next draw, okay, since you're not putting that name back in. So the probability of the first name would be 1 out of 10, or 0.1. The probability of drawing the second name would be 1 out of 9, since we already removed that first one, so there's only 9 left. And then for the third, there's only 8 left now, because we've taken 2 names out, and so the probability of the third is 1 over 8. Okay. If we want to know the probability of getting the first name right, and the second name right, and the third name right, this is and you notice the ands are capitalized. I did that just to emphasize this is a multiplication problem. Okay, so we need a multiplication rule, and you multiply these probabilities out. So 1 over 10 times 1 over 9 times 1 over 8. And if you do all that work, you should get this probability of 0.00139, right? So there's less than a 1% chance that this would happen. Okay, but that's the probability right there. Okay, so just wanted to give you an example of multiplication problem, and you know that just by sometimes they won't even use the word and, but you should realize if we are doing 3 things in a row, that requires us to do first and second and the third. Okay, so we have to slip that word in there. Okay, 4. In a test of gender selection technique, the results consisted of 224 baby girls, 12 baby boys. Based on this result, what is the probability of a girl born to a couple using this technique? Okay, once again, just basic probability here. You need to identify that sample space, which is 224 girls and 12 boys, or 236, okay, people all together. So identify the desired probability, which is they're looking for the probability of having a girl, okay, and so we divide the number of girls in the sample space by the size of the sample space, which there was 224 baby girls, right? And the sample space was 236. So 224 divided by 236 gives us this 0.9492, and there you have it. Okay, so there's the probability. Okay, whenever you do this, go back and look at the question and see if it just makes sense, right? So for this one, there's a lot more girls than boys. I mean, overwhelming so. So you know that probability is going to be super high, okay? Well over 0.9. So you should be able to just look at the numbers in here and realize, yeah, it's a real high probability that's going to be a girl, right? Okay, see if they match your numbers. Okay, for number 5, I wanted to choose this one because it has an example of the addition rule. So if one order is selected, find the probability of getting an order from restaurant A, or, highlight that, an order that is accurate. So are the events selecting an order from restaurant A and selecting an accurate order from disjoint events. Okay, so let's do this one. To begin with, it's just easier if you calculate all the totals, right? So you can go across here and add these 4 numbers, right? 324, 272, 232, and 133 to get 961. Add up 36, 57, 40, 19 to 152. If you add these 2 together, you'll get 1,113, which is the total number of respondents. And then over here, or respondents or orders, I guess in this case, you can total up the A's. So 324 plus 336 gives you 360. 272 plus 57, 329. 232 plus 40 gives you 272, and 133 plus 19 gives you 152. Add up these 4, you should get 1,113, and they should be exactly right, the same total. All right. So once we've done that, it makes things a little easier, okay? Because just like the other problems, you need to identify the size of the sample space, which is this grand total that you get from this little table, which is 1,113. And then identify the desired probability. So in this case, we have kind of an addition problem, which is the probability of A, which is an order from A. So we're talking about all these orders right over here, right? 324 and 36, or these 360 orders, plus, right, we have this second event, right, B, in which case the order is accurate, which all the accurate orders are up here on top. So you got 324, 272, 232, 133, or for a total of 961 orders there. So we're asking what's the probability of A or B, right? So whether or not the order is accurate or they're from restaurant A. And the way we do that is with the addition rule. Okay, so here's the addition rule. So once you identified that, you got the probability of A plus the probability of B minus the probability of A and B together. Okay. And we're going to see why you need to subtract this in this problem. That's kind of why I wanted to choose this one. Okay, so to do this, we can do probability of A real easy, right? Because the probability of A in this case is from restaurant A. There was 360 orders out of 1,113. So that's where this probability first comes from. We're going to add to that the probability of B, which is going to be this total over here, 961 accurate orders out of that 1,113. And then we're going to subtract out A and B together, okay, which means we had an accurate order from restaurant A, which there was 324 of those out of the sample space, 1,111.13. The reason we have to subtract that, just realize if you're trying to make sense of that, is because we already counted this one up here and it's actually been counted over here. So we were counting things twice over here. So we need to remove it once, right? And that's kind of why you are doing that right here, okay? Anyway, if you do this, and by the way, you have common denominators here, so you can just do 360 plus 961 minus 324. And then whatever answer you get there, just divide it by 1,113, and you get 0.8958. Okay, so we have approximately about a 90% chance, right, of getting this order either from restaurant A or an accurate one. So it could be one or the other, which makes sense. It would be a very high probability. Okay, now in regards to the disjoint, so event A and event B in this case, accuracy and restaurant A, right, they're not disjoint at all because the events can occur together. Okay, so an accurate order from A is very possible. What kind of events are are disjoint? Well, a disjointed event would be like saying, what's the chance that the event was accurate or not accurate? Okay, well, it's probably 100%, but you can't, right, have an order that is both accurate and not accurate, right? Those are truly disjointed events, or it's kind of like an order that was from A and from B, okay, together. It's like, no, it's just A, right? Those things are would be disjointed, the event of something from restaurant A and restaurant B. But I just want to make sure you know the idea of what disjointed is. Moving on. Okay, number 6. In a study of helicopter usage and patient survival among 59,271 patients transported by a helicopter, 156 of them left the treatment center against medical advice, and the other 59,115 did not leave against medical advice. If 50 of the subjects transported by helicopter are randomly selected without replacement, what is the probability that none of them left the treatment center against medical advice? Okay, this had enough wording to make it more difficult probably than other problems you've had, okay? But I like this one because even though this came up in chapter 4, we can actually look at how to do it as well in chapter 5, because we could treat this as a binomial too, but in chapter 4 we hadn't even talked about binomials. So let's see how to do it in kind of both ways. Okay, but just to make a point, let's look at this problem from those two angles. So first, we're going to calculate the probability that a patient did not leave against medical advice, right? That's what we're looking at. So probability of A, which is did not leave against medical advice, okay, advice. And really that probability we have, right, because it gives us that 59,115 did not leave against medical advice out of 59,271 observations. So we do that little division problem and you get us probability of 0.9974. We just note that's a super high probability that they're not going to leave against medical advice. All right. Now, okay, let's take one. This is kind of the chapter 4 version of things. You need to recognize that it's a multiplication rule because we're really talking about the probability of A and B, okay? Why are we saying that? Well, because there's 50 subjects and we're wondering whether or not what's the probability of A not leaving, right? against medical advice, and what's the probability of number 2 not leaving, number 3, number 4, number 5, but there's like and like 50 times. Okay, so it's a lot of ands. Okay, so it's definitely a multiplication. Now, the one thing you got to note in here, because there is a little tricky part of this question that talks about, throws in this thing without replacement. Okay, it's probably in here just throw you off. Okay, because we have this little rule, and if you've read it in your readings at all, okay, it's called the 5% guideline for cumbersome calculations rule, okay, which mainly says if the sample size, which is 50 in this case, is less than 5% of the population, with 50 is less than 5% of this 59,271, right, we can treat the events as being independent, okay? And I calculated that out just so you know. It's 0.008, which is much less than 0.05. Okay, so we're going to treat these events as independent. So when we look at that multiplication rule, the probability of A and B can be equal to just probability of A times the probability of B, rather than the probability of A given B. Okay, so thus we multiply probability A with itself 50 times to get the probability, okay, over and over again. And in this case, we're taking that 0.9974, right, and you use an exponent to the 50th power, so it's multiplied times itself 50 times, okay? And when you do that, you get this number 0.8779, and we are finished. That is it, okay? That's the probability of all those 50, right, where none of them leave the treatment center, okay? And that's really the probability that we were after, okay? I also want to throw this one in, and this is from chapter 5, right? Okay, just to recognize this is a binomial, since we're looking at these things as independent events. So recognize the problem is a binomial. So we can look at this as n equals 50. The p, the probability of success, 0.9974, right? We had that given to us. And q, then, which is kind of the opposite of that, would be 1 minus 0.9974, okay, which would be the probability of, say, leaving against orders, okay, rather than not leaving, which is 0.0026, okay? And I'm going to make x 50. Now, why 50? Okay, because we're defining the probability here as the probability that people are not going to leave against medical advice, right? And that's kind of what we want to do in this probability. So how many people would have to not leave against medical advice if we were going to look at all of them? Well, there's 50 there. I got to make x 50. So the probability of 50 in the binomial formula, okay, which, by the way, if you forgot the binomial formula, there it is. Okay, so we're going to take 50 factorial. It helps to have that little factorial button on your calculator. It really help you out. But this is really not that important given these problems. So when we're figuring out these extremes especially, notice what happens. You got 50 factorial over 50 minus 50, that is n minus x, right? 50 minus 50, okay, which is a 0 factorial, and 0 factorial, by the way, is 1, okay? Might not seem like it should, but it is, okay? Times 50 factorial. So all we left over here is 50 factorial over 50 factorial. This whole expression, right, which represents, by the way, the combinations that you can have these things, represents 1. In fact, there's only one way then to have all 50, right, have any of those people leave against medical advice, right? So there you go. Times the probability of not leaving, okay, against medical advice, and that's 0.9974. And we're going to raise that to the 50th, okay? And then this last part, 0.0026, which is, right, q. But notice the exponents are 50 minus 50, so you have it to the 0, and anything to the 0 is 1. Okay, so you're left with this. 1 times 0.8779, just like we got up here, times 1, or 0.8779. So whether you use the binomial formula or whether you do it up here, which seems a little bit simpler, I think, you end up getting to the same answer. But it does help to get used to this little binomial formula, so you're going to do that by the end of this. All right. 7, in a certain country, the true probability of a baby being a girl is 0.475. Among the next 8 randomly selected births in the country, what is the probability that at least one of them is a boy? Okay, so in this problem, we have that thing that says at least one, right? So first recognize that the words at least one appear in this description. That indicates that the solution will likely involve, right, using a complement. If you remember what a complement is, it's kind of 1 minus whatever the probability of that event is you're talking about. So it's kind of like the opposite of that event, right, the complement. Whatever it needs to be added to it to make 1. It's really kind of a better way to think of it. All right, so the probability of girl, which is given, right, 0.475. The probability of a boy is 1 minus 0.475, or 0.525. Okay. What we want to find is, of course, the probability that at least one is a boy. Okay. So that would include, right, we got a total of 8. The first one could be a boy, the second one could be a boy, right? The next one could be a boy, right? And then you could have more than one boy in all those choices, and maybe 2, 3, 4, 5, 6, 7. Okay. The only way, in fact, that you couldn't have at least one boy is just one way, right? And that's if all of them were girls, which there's just one chance of that happening. All right. So we can think of having at least one boy being equal to its complement, which is 1 minus the probability of all the girls, because all other combinations would fit this description, right? Okay, so we need to find this probability of having all girls. Well, since the events are independent, we can find that probability through the multiplication rule, because it's like, well, the first birth was a girl, and the second one was a girl, the third one, and the fourth one, and the fifth one, but we're using that and, right? So it's multiplication rule. So I can take that 0.475 of having girl, I'm going to raise it to the 8th, okay, because there was 8 different births we're looking at, that's our n. If you do that, you get 0.0026, right? But we're not done with the problem. That's just the probability of having all girls. If we want to know at least one boy, we just need to subtract that little thing from 1. So we take the complement of this event, having all girls, and we get 0.9974, and that is our final answer. And does that make sense, right? Because the probability of being a girl is actually lower than it is to be a boy, right? And they're close to half anyway. But if you have 8 with a near 50-50 chance, right, the probability is going to be super high that at least one of those is going to end up to be a boy. So this makes total sense. Okay. Just for the heck of it, just want to make sure you realize this is also a binomial where n equals 8. The probability is 0.475, the q, right? Which is the complement of that is 0.525. Whoops. Back up here. And we would be looking at 8 girls. Okay, so if you did that, you would get this 8 factorial over 8 minus 8, which is 0 factorial, or 1 over 8 factorial. This whole thing is going to reduce to 1, and as we know, the probability of getting all girls or no girls will always be 1. There's only one chance of that happening, okay? The number of ways anyway. And then we're going to take that 0.475 probability of girls, and we're going to take that to the 8th, right? So there's that same thing we did right here, okay? And it's going to be multiplied by the probability of having a boy, which is, there's no chance of that going to happen. So we're going to have that exponent being 0, and this ends up being 1. And if you multiply that out, you get 0.0026. So either way, then we subtract out that 0.0026, we get 0.9974. So just showing you two ways how the binomial actually works. And that binomial formula, just remember that first part is all about calculating the number of combinations you need. Now I'm going to show you that a little later. Assume that there's an 11% rate of disk drive failure in a year. Okay, for this problem, if all your computer data is stored on a hard disk with a copy stored on a second hard disk, so that we only have an N of 2 here, what is the probability of during a year you can avoid catastrophe with at least one working drive? Okay, and we'll come back to the second problem. Okay, so in this first problem, just recognize again that it says at least one appear, and that indicates somewhere in there you're going to involve complements, right? So here's what we're looking at. So the probability of failure, just given up here, 11%, which is the probability of 0.11. Just note that the probability of non-failure would be 1 minus that, and that little thing right there should be a minus sign. That's a mistake. Okay, so hold on 1 second. There, we're back. Okay. There we go. Now I changed it. Okay, so it's 1 minus 0.11 equals 0.89, right? So that's a probability of a non-failure. Okay. Note that the problem so the probability of at least one working is kind of 1 minus the probability of both A and B failing, right? There's that both thing again. Okay, so how do we find out if they both fail? Well, the probability of one failing is 0.11. The probability of A and B failing, once again, little multiplication in there, would be 0.11 times 0.11 or 0.11 squared, which gives you a 0.0121. Okay, and note that's the probability of both failing. So if we want to know the probability of at least one working, right, that means surviving here, then it's 1 minus that probability. So if you subtract 0.0121 from 1, you get 0.9879, and that is our answer. Okay, for part B, where it says at least one working, so if copies of all your computer data are stored, right, on 3 independent hard drives, what is the probability that during a year you can avoid catastrophe with at least one working drive? So they've added your N here to equal 3. Okay, so this is really not any different than the other one. We're just going to we have one more 0.11 to worry about. So it is the same thing. So at least one working is 1 minus the probability of A and B and C failing. So now we have 3 of them. Which means rather than squaring 0.11, we got to cube it, okay? Which means take it to the third or multiply it times itself 3 times. And then subtract it from 1, okay? So if you do this, you'll end up getting this 0.9987 as your final answer. And once again, does all this make sense? It should. If there's only an 11% chance of that disk drive failing and you have 2 of them, that probability is going to be greatly reduced, and it's going to be way up there. If you have 3 of them, obviously it's going to almost be fail safe, right? So you don't have to worry about that. Okay, so anyway, that is number 8. Number 9, assume that when adults with smartphones are randomly selected, 57% use them in meetings or classes. If 10 adult smartphone users are randomly selected, find the probability that exactly 3 of them use their smartphones in meetings or classes. Right? You should recognize this one as the old probability. So have your probability, or your binomial, right? This is the binomial. So you have your binomial probability formula ready. And we can go through this, right? So first, recognize a binomial with n equals 10, right? There's our 10. The probability is 0.57, right? We'll use them in a meeting or class. Q, which would be its complement, would be 1 minus 0.57 or 0.43. And then X, right? Because we want to find the probability of exactly 3 of them, okay? Use their smartphones out of that 10 is 3, right? That's what we want to know. Okay, so plug it in to the binomial formula. You get the probability of 3 is 10 factorial over 10 minus 3 factorial times 3 factorial. And once again, this expression right here is attempting to find out how many combinations of 3 can I make out of 10 different items, right? Which is going to be a lot. And if you did this, you get 3,628,800 divided by, this is what, 7 factorial, which is 5,040, times 3 factorial, which is 6, right? But if we took all this out, I believe it comes out to something like 120, okay? So it's like 120 combinations of things. Anyway, continuing on though, this 0.57, we would, right, we want that to the third, which is what we're trying to find, times 0.43, which is, right, Q, to the n minus x, which is 10 minus this 3. And when you do all that, here's what you get for each one of those values. When you multiply it all out, you're going to get 0.0604, which is the probability that exactly 3 will use smartphones in meetings or classes. Okay, so that's how it works. So it's just a simple application of the binomial formula. Just take your time, make sure you know what these factorials are, right, how to do it. So hopefully you have this button on your calculator. If not, you're going to have to do 10 times 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1 if you want. But it's not going to do any good. Okay, anyway, that's going to come out to this value, just so you know what a factorial is. Okay, anyway, that's it for this. Number 10. In an experiment, college students were given either 4 quarters or a $1 bill, and they could either keep the money or spend it on gum. The results are summarized in the table. So in this one, find the probability of randomly selecting a student who spent the money given that the student was given 4 quarters. I think in class I've said these ones really probably are your easiest ones to do. I think conditional probabilities, as long as you have a table, are pretty simple. Just keep things straight and you're good. So like before, you're probably not going to give them totals, so calculate all the totals. So 33 plus 19 gives you 52, 17 plus 26 gives you 43, add 52 to 43, you get 95, and then 33 plus 17 gives you 50, and 19 plus 26 gives you the 45. If you did 50 plus 45, you get 95, and you can double check to make sure that is the right total. Okay, so in this one, if we do A, if we use only the data for students given 4 quarters, right? So students given 4 quarters, that's everybody on this first line. Notice there's 52 of them. That's why I said 52. Calculate the probability of those who spent money. There was 33 that purchased gum out of 52. So 33 out of 52 gives you 0.6346, and you are done with that one. B is find the probability of randomly selecting a student who spent money, given that the student was given a $1 bill. All that's asking for is we're going to be given this, or only using data for these students given a $1 bill, which there was 43 of these, right there. Calculate the probability of those who spent money. This should be a who. I'm not going to go back and fix it, but anyway, sorry about that. This should be the word who. Spent money. Okay, which there was 17 out of 43, okay, or 0.3953. Okay. But yeah, these ones I like to think are pretty simple. It's just, Make sure you got this thing. Anytime you see that given, just note you're kind of dividing up your data set and only use the data that is given, right? All right, this one I'm hoping you're already pretty good at, but just really quickly, determine whether the following value is a continuous random variable, a discrete random variable, or not a random variable. And just note, to tell the difference here, almost always when you see this number of, you're going to have a discrete random variable, okay? So the number of people in a restaurant that have a capacity of 300, right? That's going to be a number, so call it a random variable, and that number will come in whole units, right? You don't have like 0.75 of a person or anything. So this is a discrete number, so it's a discrete random variable. The hair color of adults in the United States, this is not a number, right? They would be color names, okay? So it's not a number at all, so it's not a random variable, okay? The number of textbook authors now eating a meal, well, that number would be in whole units, but it is a number, so that's a discrete random variable. The exact time it takes to evaluate 67 plus 29, well, time is not likely to be in whole units, so it is not a discrete measure, but a continuous one. So this is a continuous random variable. Height is the same thing, right? Those are continuous random variables. And then the number of free dash throws. Okay. I think something was wrong in there. Oh, darn it. When I copied this over, this should have just been a dash. Okay, so free throw. Free dash long. Okay, so the number of free throw attempts before the first shot is missed, well, just note number of. Discrete random variable, think that right away. Okay. On 12, I just wanted to make sure you knew about calculating means and standard deviations of probability distributions. And it might ask you, is this a probability distribution? Well, you need to be able to add these numbers together, and if you get 1.0 in the end, you know it's a probability distribution, right? And you have numbers over here. So if it doesn't add up to 1, it's not a probability distribution. But in this case, it is. So just trust me on that. Um, we want to find the mean and standard deviation for the number of girls in a birth. So to find the mean and standard deviation, you're essentially just going to add a couple columns to this whole thing. So I'll just do that. And these are the columns you want to add, right? To get the mean, we're going to take each value and multiply it times the probability, right? So 0 times 0.005 gives you 0, 1 times 0.031 gives you this 0.031, and so on. Once we're done with that, we would sum this column, okay? If we sum that, we're going to get this mean, right? The sum of these probabilities, right, times their values will equal the mean for that distribution. Okay, so that's how that works. So the 3.988, that's our mean. Okay, once we have that mean, then what we're going to do, notice this formula, to find standard deviation, we're going to subtract out that mean from each value, so 0 minus 3.988. Okay, we're going to square that value, and then we're going to multiply it times probability, which is this 0.05. When you do all that, we get, now just take you through it, 0 minus 3.988, that quantity squared, okay, multiplied times 0.05 gives you 0.08, right? 1 minus 3.988, the quantity squared, okay, and then we subtract out, times the probability, 0.031, gives you this 0.28. Anyway, you do that for all these numbers, add them together, sum them up, and you would get 2.03. But note, that's a variance. To get standard deviation, we've got to get the square root of that. And you take the square root of 2.03, you get 1.42. And that's all this problem wanted. Just that's how to get a mean and standard deviation from a probability distribution. Okay, 13. Just more work with binomials. On this one, um, based on a poll, 69% of internet users are more careful about personal information when using a public Wi-Fi hotspot. What is the probability among 3 randomly selected internet users? At least one is more careful about personal information when using public Wi-Fi hotspot. So once again, notice that this thing used the words at least one, so the probability answer probably involves a complement, and also recognize the problem represents a binomial. Okay, so we got P, which is probability of being careful, it's 0.69, right? That's 69% up there. Q, which is 1 minus 0.69, would be 0.31. Okay, N is 3, so there's that 3 right in here. Okay, and then we're going to choose X as 0. Right? Now, why would we do that? Okay, because we're after the probability that among the 3 randomly selected internet users, at least one is more careful. So if at least one, that's going to include 1 and 2 and 3. The thing it won't include is 0, right? So we are just going to calculate that probability of 0. So if we plug that into the binomial formula, there we go. You get the probability of 0, which is kind of a nice number because we know this first part's always going to end up to be 1. Okay, so 3 factorial, which is 6, divided by 3 minus 0 factorial, which is 6, times 0 factorial is 1. So you have 6 divided by 6, or 1. Okay, you didn't believe me. That's true, though. See, it's 1. Okay, times 0.69 raised to the 0 power, which is 1. Okay, and then we're left with this 0.31 cubed, right? Raised to the third. So when you do that, you get 0.31 cubed, or 0.029791. But remember, that's not our answer. That's the probability, okay, of getting none of these people, right, to be careful. And we just want probably at least one. So we just subtract out that little probability from 1 and get this 0.970209. Okay, which should make sense that it's a very high number since 69% are more careful, right? And so if we have 3 people and just at least 1 to be careful, that number is going to be way higher than that. Okay, so it makes sense. All right, one more problem and then we're done for now. But assume that random guesses are made for 9 multiple choice questions on a SAT test, so that there are 9 trials. Okay, so that is 9, each with a probability of success. Okay, given by p equals 0.45, and find the indicated probability for the number of correct answers. So we're going to find the probability that the number of correct answers is 4. Okay. Sorry about that X, that slipped in there too, and find the probability that a number is fewer than 2. Okay, so here we go. It's binomial formula time. So recognize that it's a binomial, and for A, you had n equals 9, p equals 0.45, right? It's given to us. Q would be 0.55, which is 1 minus 0.45, right? And then we want to know the probability is 4, okay? So to get that, the probability of 4, we take n factorial, which is 9, right? 9 trials. Okay, 9 factorial over 9 minus 4 factorial times 4 factorial, right? And this will give us the number of combinations you can make of 4 things out of 9 things, right? So calculate that one out. We're going to multiply that times 0.45 to the x, which is 4, and times 0.55, which is q, to n minus 4, so 9 minus 4, which is 5. Okay, and if you do all that, okay, I'm going to let you do the math on this. We've done enough there. It's 0.2600. Okay, and that's our answer. For part B, we're doing the probability that x is less than 2. Okay, and just note that to do that, there's probability of 1 would be included, and the probability of 0 are both less than 2. So we need to find those two binomial answers, right? So we're going to do the probability of 0, and we're going to do the probability of 1. Okay, we're going to put those numbers into this factorial, this binomial formula. And for 0, this is what you get, right? 9 factorial. And once again, we know this is going to be 1, okay, because it's a 0 there. There's only one way to have none of them that way. So 9 factorial over 9 minus 0 factorial times 0 factorial, which you're left with 9 factorial over 9 factorial, 1, times 0.45 to 0, which is 1, and then times 0.55 to the 9, which is 0.0046. Okay, so there's our one probability for 0. For the probability of 1, well, we just throw that in there. So we have 9 factorial over 9 minus 1 factorial, or 8 factorial, times 1 factorial, times 0.45 to the first, right? Okay, which is 0.45, and times 0.45 to the 9 minus 1, right, which is 8. Okay, which if we do all that, we get 0.0039. So the final answer then, we've got to add those two together. So 0.0046 plus 0.0039 gives us 0.0361. Okay, and there you go. Does this make sense that this would be so small? And I would always kind of go back and just see if that makes sense to you. Well, there's 9 trials, right? And you're looking for the probability that the number of correct answers you get is less than 2, right? And you have a 0.45 chance of being right, right? If you had 9, if you have a 0.5 chance, right, you expect to have about 4.5, right? And there's 9, but it's definitely going to be less than that. But yeah, it'd be a kind of an extreme thing to have a 1 or a 0, right? So that number is a very extremely low chance, so it does make sense. Anyway, take it through. I hope this helps you out a little bit. If you need something more, just ask me. I'll be glad to go over things with you.